Welcome to piano lecture number 8. At the start of these lectures, I promised that we would create accurate models of the Boeing 787 and the Airbus A350 from a common origin. Having now completed the 787, in this lecture we will put together the A350 in short order, based on the same generic design that we assembled in lecture 6. Before we start, let's look at an existing file from the piano database for an initial definition of the A350. The V15A is an early piano model representing a preliminary understanding of the type prior to entry into service. Let's load it. Its certification weights match weight variant 000 in the April 2015 ACAP. The OEW is merely a first estimate, typical of some airline analysis. This plane carries 315 passengers over a range of, let's say, 7,270 nautical miles. We will now go back to our common origin, the generic 250-seater from lecture 6, modify it appropriately, and then resize it using the optimizer to match the A350 V15A performance. So let's do all of that. This is how the generic plane looks. Change passenger count to 315 seats. Fuselage geometry. Up the width from 5.8 to 6.0 meters. Fuselage length for the A350-900 is 65.3 meters. Without changing the fuselage shapes, I can make the front just a little bit more blunt and set front fuselage length to 10 meters. Leaving the rear at 20 meters. Mid-fuselage length must now be 65.3 minus 10 minus 20, 35.3 meters. I will keep the existing rubber engine model, so that means still the high BPR notes advanced. I will also retain the nacelle scaling connection between nacelle width and reference thrust, and you may just remember that we initially associated a 12-foot wide nacelle with 70,000 pounds of thrust. We can stay with our existing nacelle shape as well, although I can modify some proportions, for example to match the settings in V15A. I will need to temporarily turn nacelle scaling off, change nacelle length over width from 1.5 to 1.6, let's say depth over width to 1.05, turn nacelle scaling back on. The actual fuselage and nacelle contours are of course subtly different between the 787 and the A350, but we will not try to generate new shape files specific to each type. Wing geometry. Move the planform brake fraction a little bit inboard to 0.25. Reduce sweep back very marginally by, say, half a degree to 32 degrees. I will keep all our thickness chord assumptions unchanged and reset winglets to 45 degrees as a gesture to the actual smoothly curved wingtips. Tail. Look at the geometry report. For the stabilizer, that's horizontal tail, we have at the moment an aspect ratio of 5 and a tail volume coefficient or V bar of 0.9. I will set an aspect ratio of about 4.25 and a V bar of around 0.82. For the fin, we have an aspect ratio of 1.5 and V bar of 0.05. I will increase the aspect ratio to about 1.7 and increase the V-bar to 0.06. And by the way, if you are an aerodynamicist, the V-bar reference definitions are trapezoidal. Passenger weight is currently 210 pounds. Let's set 95 kilograms, since this is a European aircraft. Max payload over design payload is purely a design choice. Our original value suited the 787. A lower value around 1.6 is more typical, and I will set 1.62 just to line up with the V15A model. It may be, for example, that with the 787 there was some early emphasis on cargo or anticipated stretches. In fact, from the Dash 8 to the Dash 10 is a 20% stretch. From the 350-900 to the 1000, it's half that. I will reset contingency fuel to 3%, which is a common assumption with modern flight planning, and I will return to the question of assumptions. And finally, with a little bit of foreknowledge, I will apply an arbitrary overall drag factor of around 1.5%, just because this is what will get us to the right numbers for the V15A. Our aircraft now looks like this, and has a range of this much, which of course is not the number that we want, so we are now ready to run a design sizing optimization. Set the variables: MTOW, wing area, thrust and aspect ratio. We can leave everything as it is. Constraints: range of 7,270 nautical miles. I will specify nominal 9,000 foot field lengths, just as we did for the 787, and we don't expect the landing field length to be active. Our objective will be to minimize the MTOW, and let's get started. I've now let this run for about 4 minutes, and that's good enough. Check the range, 7,270 nautical miles. Field lengths, TOFL 9,000 feet, and landing field length, as expected, not a problem. This is how the aircraft looks, and let us now save it. And I will call it our lecture 8 A350A. Comparing the result of this sizing exercise with V15A, this is V15A and A350A. We can see a very good match. Spans, wing areas, and all the weights are very close to each other. The only noticeable difference is in the geometric fuel capacity, which in the V15A is limited to 138 cubic meters according to the 2015 ACAP, but even that is only because some of the wing has not yet been opened up to fuel. Piano thinks that there is enough space in this wing for 162 cubic meters. and our payload ranges overlap, with the exception of the part that is limited by fuel capacity. This is certainly a good start. However, V15A is just an early estimate, and there are no payload ranges published yet in the 2015 ACAP that we might compare against our results. In any case, a direct file comparison can show us how few changes we made so far to our original generic baseline. This is the generic aircraft, this is our A350A, and these are the changes that we just implemented. So we are finished with the sizing exercise, and we can now move ahead and set some of the actual basic geometry and certification weights, just as we did previously for the 787. To do this, we will use a later version of the ACAP from June 2017. We have reverted to our A350A. We can turn nacelle scaling off now, and we might as well set the tail areas. Wing geometry, we will set an Airbus wing area of 443 square meters. Overall span 64.75 meters. ACAP fuel capacity is now given us 141 cubic meters. Our wing can potentially hold up to 165.2. Set 141. Geometry report. Airbus area 443 square meters, 64.75 meters overall span, 141 cubic meters of capacity. Setting our passenger count now to 325 passengers, we can apply the increased certification weights for weight variant 10. So we have MTOW of 280 tons, MZFW 195700, maximum landing weight 207,000 kilograms. I will set a representative OEW of 142.3 tons, and in fact this choice is also consistent with the maximum payload of around 53.4 shown in the ACAP. I will make no changes to the engine other than increase the takeoff rating a bit to match a quoted value of 84,000 pounds of available thrust. Use a factor on takeoff rating, setting that to 84,000 divided by our current value of 82,238.8. About a 2% increase. Let us run the range. Roughly 8,100 nautical miles with 325 passengers. Looking at the field lengths, the TOFL in the 2019 ACAP is around 9,670 feet at ISA plus 15. I can leave it as it is, or set the takeoff CLmax factor, let's say, to 0.99. And we get this field length. The nominal approach speed target is 140 knots at 205 tons or 141 at 207 tons. We have a VAP of 138 knots. I will apply a factor on the landing CLmax of 0.96, and that should get us there. 141 knots. Landing is by its nature less predictable than VAP, and the LFL in the ACAP is a bit longer than this. Piloting techniques, systems and braking qualities are all unknown. For example, if I reduce the touchdown speed ratio to just below 1.1, let's say 1.08, which implies a more prolonged hold-off, that gets us to the ACAP value of around 6,500 feet. Take a look at our plane as it stands at the moment, and we can now save this as A350B. Let's look at our plan view, and if we overlay this on an actual view, we get this, and that is a reasonable match to the geometry of the A350. This time we can also compare our model against published payload range characteristics in the June 2017 ACAP. Our payload range, the same picture, add an overlay, so we have an excellent agreement. I should say at this point that manufacturers in general make it abundantly clear that ACAP data are provided for information only. Not all relevant operational assumptions are available in such documents, and indeed there is no requirement for them to be. And they cannot be assumed to be consistent between manufacturers or between types. So let me just say that if we make the particular assumptions that we have made, the resulting match is clearly good. Let's get back to piano. To get closer to current in-service levels, we can consider the May 2020 ACAP. Staying with weight variant 10, we keep the same certification weights. Indications are that there has now been a slight reduction in nominal OEW, together with an increase in fuel flows. Let's try some appropriate changes. I will reduce the OEW by around 400 kilograms to a typical value of 141.9 tons. And this happens to be consistent with a maximum payload of around 53.8 tons in the ACAP. I will also apply a couple of minor tweaks. These are the same refinements that I already made to our 787 model during Lecture 7. Reset this empirical coefficient in our compressibility method from 0.12 to 0.15. And modify the user adjust CL/CD curve, which at the moment looks like this, to make it a bit more peaky around the minimum. And shift it a little bit to the right. And I could instead have copied and pasted these two settings directly from the 787 as I've shown you before. Now, one candidate for adjustment is aeroelasticity. Let's add a simple one via user aeroelastic drag curve. If we take a quick look at cruise weights, at the lighter weights, let's say around 180 tons, we will make no adjustment, and at the highest weights, say 280, a 3% adjustment. 180,000 kilograms 1, 280,000 1.03. And I will just leave it linear in between. This is no more than a rough guesstimate, and it lies somewhere between the two different positions that we adopted in Lecture 7 for the 787. Finally, we will arbitrarily increase the user factor on total drag by another 1% to 1.025. So doing a range calculation, range is down to 7974 nautical miles, or let's say just under 8,000. We will save this aircraft as A350C. Run the payload range again. This is what we get. And this is the same picture. Overlay the 2020 ACAP. And we are now quite literally within line thickness reading tolerances. An optional higher fuel capacity is also shown in green. This corresponds to 166.5 cubic meters and gives a ferry range of nearly 11,000 nautical miles. If I set that in piano, 166.5 cubic meters, repeat the payload range, it matches up just as nicely. The A350 ACAP payload range diagrams do not include reduced weight information, so we cannot pick out and compare interior points as we did in the previous lecture. Instead, I will simply show you some of Piano's spot point predictions of fuel flows along a typical flight. Mach 0.85, 35,000 feet, and let's say 260 tons. Fuel flow is 6,740 kilograms per hour. Go up by 2,000 feet to 37,000, reduce by 20 tons, 240 tons. Fuel flow 6,210 kilograms per hour. 39,000 feet, 220 tons. Fuel flow 5,720 kilograms per hour. 41,000 feet, 200 tons. Fuel flow 5,260 kilograms per hour. If I go down to our lowest weight, 180 tons, 4,820 kilograms per hour. If you are able to check some of these independently, you will probably find that they are within 1% of nominal expectations. I will finish our modeling of the A350 at this point. To summarize, as promised in the first lecture, we have now created substantially accurate models of the Boeing 787 and the Airbus A350 from a common origin. We defined that shared origin earlier from scratch as a design exercise in Lecture 6. All our planes are now encapsulated in tiny files of less than 100 parameters each. All our planes share the same generic rubber engine. We can consistently compare settings and assumptions between them, and it is actually surprising how few differences there are in our files. Let me show you. Looking at the early models, so our Lecture 6 Boeing 787 and our A350A from today. These are the only differences in parameters. And looking at the more refined versions, Lecture 7 Boeing 787 and our A350C from today, still not that many differences. Everything that we have done is transparent and reproducible. All these models can be recreated in full and/or modified by any piano user, and all results can now be verified by anyone with access to good information. Although we can examine and change all the assumptions in these piano models, we cannot do that with the manufacturer's public performance claims, and I will therefore steer well clear of Airbus versus Boeing arguments or attempts at market comparisons. Before I wrap up, I'll make a quick detour to say a few words about NOx, hydrocarbon and CO pollutants. Recall that direct CO2 emissions are simply proportional to fuel burn. Every gram of aviation fuel that we burn produces around 3.16 grams of carbon dioxide. This does not apply to pollutants other than CO2. There exists an ICAO engine emissions data bank in the public domain that gets updated occasionally by EASA, and it gives emissions of nitrogen oxides, carbon monoxide and unburned hydrocarbons. Regulatory data are only published at 4 thrust settings at sea level. They are extrapolated to in-flight conditions throughout the industry via a simple set of corrections known as the Boeing 2 method. Because only 4 regulatory points are given, and because such points can be very irregular, the practical usefulness of the data is limited and potentially vulnerable to gaming. In any case, the methods are built into Piano. You can enter or adjust your own emissions indices for any engine, and importantly, you can insert intermediate points to control the interpolation if you want to. NOx, hydrocarbon and CO indices given in Piano are for information only. I'd like to stress one last point that should already be clear. Engine performance characteristics from Piano's rubber engine models are completely independent of whatever NOx, hydrocarbon and CO emissions indices you choose to apply. The only connection is that fuel flows from the models are used to evaluate the indices throughout the flight. Let me pause here. In future lectures, we will also turn Piano's focus to examples of a rather different kind, a business jet and a turboprop.